So how do contrast agents work for MRI? Remember we had discussed contrast agents for computed tomography, that they change the effective Z of tissue and therefore the linear attenuation coefficient. And so how does a contrast agent MRI work? And essentially we distinguish two classes of contrast agents. The one are those that act on T1, it's paramagnetic agents. These paramagnetic agents, the interaction as it is done is very complex, it's difficult to understand, but essentially the picture that we have is that this is an interaction of the contrast agent with surrounding water, its own molecular tumbling, and how fast the water diffuses and how close the water diffuses close to that paramagnetic agent. So that's the molecular picture. Phenomenologically, the way they are described is that the T1, 1 over T1 in the presence of the contrast agent is given by 1 over T1 in the absence of the contrast agent, plus a term that is the contrast agent concentration times this factor R1, and this factor R1 is the relaxivity of this contrast agent on T1. It in a way describes what concentration of contrast agent one needs to generate a change in T1. So it allows us, it is a phenomenological equation, and we'll stick with this. So to give you an idea for a typical parameter here, if we take a contrast agent concentration of a millimolar, a relaxivity of 3 per millimolar per second, and a T1 in the absence of the tissue in the absence of the contrast agent of 1 second, then we can plug these numbers in and we'll actually calculate that the T1 in the presence of 1 millimolar of this particular contrast agent changes from 1 second to 250 milliseconds, or by a factor of 4. This is a huge change in T1. Imagine you're doing your image at a TR of 250 milliseconds, the T1 of 1 second, this will create a very dark image, but then you're close here to the optimal repetition time at this point, and the image, the signal intensity will increase drastically. So if we look at the signal, and now in this case on T1 weighted image, it's proportional to the Z magnetization, so it's T1 weighted. We're looking at this expression here, and we have assumed here for the experiment that the TE is much shorter than T2. This is in the absence of the contrast agent, and in the presence of the contrast agent, the recovery to thermodynamic equilibrium is much faster. So if we measure at a relatively short TR, the signal becomes bright in the presence of the contrast agent. So these paramagnetic agents, they lead to a brighter signal on T1 weighted images. The other class of contrast agents are paramagnetic and susceptibility agents. They act on T2 and T2 star. The T2 star agents are called susceptibility agents. So if we look here, actually the expression that describes the effect on T2 star has the same expression that we have for T1. It's the effect of the contrast agent concentration, but now we just have the proportionality here is the relaxivity R2 star. So what happens with the signal as a function of TE? The signal is proportional to the transverse magnetization. This is in the absence of a contrast agent, that's the T2 star with a gradient echo, and in the presence of the contrast agent, we have a T2 star for CA, that's this T2 star here, a faster decay. So to give you an idea, we take again a contrast agent concentration of a millimolar, a typical relaxivity of 50 per second per millimolar, and a T2 star of 50 milliseconds. We calculate now, and with this concentration, we calculate that now the T2 star is 14 milliseconds. So we go from 50 milliseconds to 14 milliseconds. Now imagine what happens. You're measuring at a TE of 50 milliseconds. Now the contrast agent comes in at a concentration of a millimolar. The T2 star is reduced to 14 milliseconds. At the TE of 50 milliseconds, you no longer have a signal. So while you were optimal for the absence of the contrast agent, now the signal has decayed. And this basically leads to a reduced signal in the presence of the contrast agent for the T2, for the paramagnetic and susceptibility agents on T2 or T2 star weighted images. And that is because we are measuring somewhere here at a more prolonged TE. So paramagnetic agents produce brighter signal because they act on T1. Paramagnetic and susceptibility agents, which act on T2 and T2 star, they produce reduced signal. So let's look at some examples of contrast agents. First, some properties. They are typically restricted to blood. They are ideal to image vessels. or leaky vessel walls, such as what we see in tumors and inflammation. So here we have an example of the mouse vasculature. We have an MRI of the mouse trunk, so this is before contrast agent application, and this is after. We can see a change here clearly in the trunk where the contrast agent has gone. This is an example of brain. There's a malignancy in the brain, and the before the contrast and after the contrast, we can see difference. We can see here the rim that lights up. This tells us that there is a breakdown of blood-brain barrier, which is typical for the tumoral edge. Still very well vascularized, but breakdown of blood-brain barrier. You can also see here that lots of the vessels, the bright stuff that lights up, these are vessels that carry the contrast agent. So this is a predominant way of enhancing leaky tissue. Here is now an example of contrast agent application before contrast and after the contrast, and we see here the liver, and the liver is now suddenly becoming dark. This is a susceptibility agent. It's a T2 star agent. That's iron oxide in this particular case, and it has produced negative contrast. So here we have positive contrast, positive contrast, positive contrast, and here this example of a T2 based paramagnetic or susceptibility contrast agent like iron oxide is producing negative contrast, so signal is reduced. Second example that I want to talk about are intracellular contrast agents. They're much harder. One is manganese. Manganese is paramagnetic. It shortens the T1. It has the interesting feature that it's transported by calcium channels and therefore shortens the T1. So this has been used in among others in brain imaging. This is an image of a rodent brain, and we can see here very nicely the structure of the hippocampus, the different areas, CA3, the denti gyrus, etc., corresponding to the structure seen in histology. Prior to manganese, these T1 weighted images look fairly uninteresting. After the application of manganese, one can see a fairly substantial contrast, which reflects the activity, the differential activity of calcium channels in the brain by region. Now, manganese as a contrast agent is not used in humans. It has toxic issues of toxicity, but in neuroscience, it has become a very interesting and promising tool to look at fundamental neuroscience questions and also other questions. Now, another thing for intracellular contrast is a bit particular that I want to mention, that is the imaging of transplanted cells or stem cells. So what is done here is, for example, that the cells that are injected are preloaded with contrast agent. So within them, they contain the contrast agent. And then one looks at the change in MRI signal as the cells are being injected and then migrate within the body. And this is an example of transplanted Langerhans cells in the liver. So lung transplantation of islets is a recent form of treatment of type 1 diabetes. These islets are injected into the patient, and one of the questions here was where do these transplanted islets go in the body? There has been a suspicion that they would end up in the liver, and indeed what these images show here are the islets. They show up as dark because they are, in this case, they were used with a paramagnetic, with a susceptibility contrast agent, so a T2 contrast agent or T2 star, and they are indeed showing up here dislodged in the liver, where they are making their action on the body by helping to secrete insulin and therefore reduce the effects of type 1 diabetes in these patients.